Hello everyone, welcome to the Tim Station YouTube channel. I assume if you're watching this video, you've seen the video over on my main channel where I build this Stirling engine and mounted it to a bike, with the end goal of the Stirling engine powering the bike with a cruise speed of 15 miles per hour. That requires an output of about 100 to 150 watts, which it's very far from outputting currently. However, I wanted to make this video to show you some of the design considerations and constraints I had when coming up with a design of this engine. So let's hop into CAD and show the design. In the video I said that I wanted the engine to be as large as possible because Stirling engines have very little output power for their size. Now it had to fit within a bike frame, and as you can see from the design there's still plenty of space within the bike frame. However, that wasn't the only size constraint. I also need to fit a burner on the front of the engine, which will go somewhat in the front of the frame there, and I'm probably going to go with an alcohol or methylated spirits burner because it's a lot quieter than the propane blowtorch burner, because I want to hear the engine running rather than the roar of the flame. The other constraint is that my CNC milling machine can't cut any deeper than 50 millimeters. This isn't a constraint of the machine, it's actually the cutting bits that fit in the spindle don't come in lengths longer than 50 millimeters. So for example, the piston stroke here, that cylinder can't be longer than 50 millimeters, which if you subtract the length of the piston, reduces it to about 30 millimeter maximum travel. The displacer cylinder is slightly different because you can stack two cylinders together for the cold side and the hot side, so that's actually 100 millimeters in length. The reason why the cylinders are stacked so close together like this, instead of being separated by a gap and then a small tube or channel for the air to flow through, is because you want as much air in the engine to be heated and cooled as possible. Any air that isn't being heated or cooled is just wasting energy. It's creating an inefficiency in the engine. For example, the air between the cylinders here, there's a small volume here. I tried to make it small as possible, but this air here doesn't do any work. And also any air that's around the side of the displacer, in theory doesn't do any work. It does actually get heated and cooled by the outside of the cylinder, but it's still a slight inefficiency. However, that will be fixed with a later modification. Moving on to the calculations for the engine, I have this page, which is simply just the engine parameters, such as the displacer and power piston dimensions, and I've entered them all in for the final working engine. So the displacer travel is 40 millimeters, and the power piston travel is 25 millimeters. This gives me stuff like the swept volume, which is basically the air that moves either side of the displacer. So as it moves from the hot to the cold side, it's this volume here, and then back again, and this volume here. And it gives me stuff like the compression ratio. But the thermodynamics for the engine and calculations are on this page. On the left is the crank angle, and 0 degrees is when the piston is at top dead center, or in the CAD model all the way to the left. And the displacer, piston and travels aren't actual values, they're just ratios. So when the piston is at 1, that means it's at top dead center, and the displacer is halfway down the travel. Then when the power piston is halfway down the travel, the displacer is all the way at the bottom, so it sort of leads by 90 degrees, which you can probably see when the engine is running. The temperature is a basic calculation based on these minimum and maximum values I've entered here. It's very hard to measure the actual temperature of the air inside of the engine. The 90 degrees is simply the outside temperature of the cold block that I measured after a run. I measured the outside of the hot block and it was only saying about 280 something degrees. However, when it's glowing red hot, steel, it normally starts to glow red hot about 500 Celsius or higher, so I thought I entered just 500 Celsius there. Also, all the units for the calculations are done in Kelvin for temperature, pascals for pressure, and cubic meters for volume. I've adjusted them in this table just so they're easier to read, because when you start doing the engine volume cc in meters cubed, it becomes very small decimal points. Actually, I've got something wrong there. That should be cc there. So yeah, it shows the temperature variation throughout the cycle, the engine volume throughout the cycle, the air volume throughout the cycle, the gauge pressure, so that's the pressure inside the engine minus 1 atmosphere. And then I've also put it in PSI for you Americans to read a bit easier. The torque calculations I'm not quite sure about, but I've literally just multiplied the pressure by the diameter of the area of the piston times the crank offset. But anyway, all of this basically is used to calculate this graph over here, which is the Carnot cycle. The theoretical best thing is to follow this, this kind of rectangle, parallelogram, parallelogram. So you have the heating on this side, where the air increases in pressure. So pressure's on the y-axis, volume's on the x-axis. So you heat it here, the air pressurizes here, and then you expand it as the piston, the power piston goes down. And then you cool it here, so the pressure drops, and then you compress it back up here. Now, in reality, due to the crankshaft dimensions and offsets, it looks more like this oval here. And this is an absolutely, 100% efficient design, I guess, which obviously doesn't take into consideration any frictional forces or, leaks around the piston. So this is a 100% ideal situation. And with my current entered values, you can see up here, power output of 5.23 watts. That's an absolutely ideal value. So, yeah, 5 watts is not looking great. However, if we input 200 RPM, which is the final test when I had the flywheel running, so we get rid of the resistant forces of the bike wheel, so we entered 200. We, in theory, produced 14.52 watts. Now, that's also ignoring all the frictional forces, so, yeah, it's not the most accurate calculation. But there's one major thing I forgot to take care of during the build, which I think will drastically improve the efficiency of the engine. And that is that I didn't make sure the displacer is airtight. So, if we were to simulate a non-airtight displacer, that would be the same as basically removing its volume so that it is counted in the overall volume calculations. And that almost halves the power output from 14 down to 8.5. So, basically, just by sealing off the displacer, which I need to do very soon, should almost double the output, in theory. Another way to increase the power output is to increase the pressure inside of the engine. So here I have the atmospheric pressure inside of the engine, and if I double that, so I put 2 atmospheres in, we in theory double the output power. So you can see now it's 29 watts, went from 14 to 29 watts. And I designed this engine to run on 7 atmospheres of pressure. That's 7 atmospheres above 1 atmosphere of pressure, so that's 8 atmospheres, or roughly 100 psi gauge pressure. Which should massively increase the power output. As you can see now it's at 116 watts. The issue with this is that to heat and cool the air by nearly 400 degrees Celsius at 200 RPM, if you see it's 500 maximum, 90 minimum, 410 degrees, requires a heat input of about 2.8 kilowatts, which is far too much. The propane torch is probably 1 to 2 kilowatts. So this is where a regenerator comes in. A regenerator is usually a high surface area material like some kind of steel mesh or wire wool, and it's mounted between the hot side and the cold side of the displacer cylinder. So on my engine, I'm actually going to mount it around the displacer piston, so it's going to move with the piston. The idea is that as the hot air is at this side of the engine and the piston moves, it will flow around the displacer to the cold side. As it does this, the high surface area steel mesh will absorb some of the heat, so it will heat up itself. And then as the air cools down on the cold side and then flows back around the displacer, it will then recycle some of this heat, so then the wire mesh will actually heat the air going back to the hot side. So it sort of stores the hot air, stores and then recycles to the cold air. It stores the hot air, heats the cold air. That should hopefully reduce the amount of input power I'll need. So I won't need 2.8 kilowatts. I don't actually know how much I will need, but that's something to experiment with. The other thing to note is that with this higher output power of 116 theoretical watts, the engine will most likely spin faster than 200 RPM. So let's say it now spins at, I don't know, 1500 RPM. So now you can see, trying to heat the air by that much temperature difference at that RPM with that pressure, we're looking at 21 kilowatts of heat energy, which is not possible with an alcohol burner sitting between my legs on a bike. So it's probably likely that air will then not heat up as much to, let's say, 150 Celsius. So yeah, that's about right. It will cycle between 90 and 150. And that will give an output of 127 watts, ideally. With the water-cooled cold side of the cylinder, I'd like to get that down to maybe 50. So then we have, well, it's probably be a bit more than that. Let's say 70. I have run some tests with a methylated spirit burner by simply heating up some water, and I've managed to achieve several hundred watts without any heatsink design. So I think like a nice, a well-designed copper heatsink above the flame should be able to capture hopefully a kilowatt, and potentially more if I make it larger. Which is probably similar to what the blowtorch does, but the heatsink should be able to absorb a lot more of that heat. Anyway, I thought I'd make this video as a reference for anyone that wants to build their own Stirling engine, or anyone that wants to give advice for my Stirling engine. The next steps are to make the displacer completely airtight, so we're not wasting any energy there. Water cool the cold side of the displacer cylinder. Test some different crank lengths, and then finally pressurize the engine to see if we can get some more power. So, thank you very much for watching. I'll see you in the next one.